Okay, I think we will start. And if you look at, this is the last page of chapter 3, and actually we're going to finish chapter 3. So if you look at this one, there are a couple of errors which I want you to correct. First of all, this is from a different textbook. It was the closest thing I could find that will sort of like wrap everything up together. So the first thing to note is, do you understand what they mean by saying y is normal sub n x beta sigma square I? So this is just a very compact way of saying three things. One, it is saying that the y vector has n observations. They have what's called a multivariate normal distribution, but we don't have to go into of that one. It just means individually everyone is normally distributed. Together they have what's called a multivariate normal. Right? There's n rows. The sigma square I think should be familiar, because what does that say? We know that in the linear model var y is sigma square I. The class gets that. So this, every time you see a normal distribution notation, it's always mean variance. But it's just that this is for vectors, that's all. So this vector has variance sigma square I. That's what this means. Is it confusing to you why the mean of y is x beta? Isn't it correct? In a linear model, what does it say? A linear model says y is x beta plus epsilon. Once again, what happens if I take e to everything? This is constant, so I get this. And by assumption, e epsilon is 0. So as I said, this is a compact way to say three things. That the mean of y is x beta. According to the model, the variance of y is sigma square identity, and there are n observations. Okay, so we have all that. The other thing is, don't we want to estimate beta? Yes. So we estimate it by using the v-square estimator called beta hat. Now they use s square here, which I'm fine with. When they say corrected for bias, let me ask you whether you remember. How do we estimate s square for any linear model? Can you give me, in terms of the word resid, somehow? It's always what resid? Do you remember? How is s square estimated? It's a fraction of something over something.
N minus.
Very good. It's over n minus. Yes, very good. I'm not sure how well known this symbol is. I've seen it a couple of times. Some would roll, but rank x. Yes, that's right. Very good. But what goes on top? What about the resid? What is the thing that you have here? Yes, perfect. So s squared, you can add that to your notes because it is not stated. So when they say corrected for bias, it's actually this. This is trying to correct for bias. If you just divide by n, yes, you get something okay, but it's biased. That's why we do this. And there's a second reason why we do this. When you do it like that, then look at point 2. I'm going to go to point 1, but look at point number 2. There. Now this book uses, they are still talking about where x is n by b of rank k. All right. So they do say that this is of rank k. So what are we saying? Can you see? This is the very, very important summary. When you take n minus rank x and multiply by s squared over sigma squared, this has that famous chi-square n minus rank x distribution. I hope everything is fitting together now. And you can use that to make confidence intervals to hypothesis tests, because you know the main distribution of s squared. All right. The third fact is that beta hat vector and s squared are independent. That actually is something that you just need to know. We are not going to prove it. Right? Now, point number one has so let me just very quickly go through what I just went through with the class. I told them that saying y is nx beta sigma square I is saying three things. It's telling you that your y vector of observations or response values, that there's n of them. It's telling you that they are all jointly normal. Every individual observation is modeled as normal. The vector itself is also what we call multivariate normal. Now we don't cover the multivariate normal in this class, so we will not go there, but just take it to mean individually they are all normal, together they are normal as well. And there's n of them. This is saying, see, we know that normal distribution notation is always mean variance. And we know very well by now that a linear model has variance y sigma square I. We also know that the linear model, actually, this is not even stated in the notes. Can you add this line? In general, a linear model is this. Vector y is x beta plus epsilon, where we assume the expected value of epsilon is 0. It's nothing. We also assume var y is sigma square I. This one the class gets right all the time. Very good. That's it. So you can add these lines to the notes, right? It's impossible to find one statement in the textbook that does everything we want. So we just add some stuff to it. Linear model is y equals x beta plus epsilon. The assumption is that the epsilons have a 0 mean, which leads us to know that EY must be x beta. And then how do we estimate S square? I was telling the class, when you say correcting it for bias, it means dividing by not n, but n minus rank x. In the case of simple linear regression, the rank of x is 2. All right. Okay. So let's just say there's one error I want you to correct. Look at point 1. Does anyone detect something strange about it and something that's probably wrong? This says beta is normally distributed like that. Does that make sense? Is beta random? Beta is not random. Beta is fixed. So please add a hat. Beta hat. Right? The beta hat thing that you estimate, and in fact, this is good revision as well. Does anyone remember what is the general form for beta hat? Actually, it's in the group book I just returned, but I wonder whether you can quote it from memory. What is beta hat? How do you find beta hat? Beta hat is something y, right? You can check your group book, that's fine. It's
all that inverse time action.
very good. Very good. And that you can add that as well. It's not there. And that is why beta hat has randomness, because beta hat is a function of something fixed, but something random. That's why it has a normal distribution itself. So I'm not sure why the textbook wrote it this way. I think I was trying to make something more general. You see, something kind of strange. X prime x inverse x prime x. Can you just cancel that? X prime x inverse times x prime x is just going to be identical. So what are you saying? We are saying that the expected value of beta hat is, can anyone tell me, in a linear model, if you find beta hat this way, then the expected value of beta hat is it clear from the notation? Beta. This is what we call an unbiased estimator. You know why? Because in the long run, it gives you what you want. And that closes chapter 3. This summary sheet, it took many weeks to build up to this, but here we are. This is essentially everything you need to know about linear model, and you should be able to do every question in the homework. Right? Of course, please come see me, problem, but in theory, everything has been introduced. Is this okay? Okay, so please correct these errors, okay, beta and hat, and you can cancel this, although it's not mathematically wrong, it's just introduced. I'll tell you what, okay, I'll full disclosure. The book actually did this as x prime x like that. I'll just give you one small detail. What is this? This is a generalized thing. It's for evil cases where x is not full rank and bad things happen and there's no inverse, but there's a generalized inverse. But in general, we are not going to deal with problematic cases like that. And generalized inverses become inverses when it's non-problematic and therefore this. So in other words, the textbook is giving a very, very, very general. They actually put it as a minus sign. I added a one there to make it better. But that's way beyond this class, so we will not go. You can just cancel. Okay, let's start on chapter 4. There is a batch of notes which I have prepared. We will go through most of it, and of course, I will point where we do not want to talk about. Okay, this you can see the source. You can download the whole book for yourself if you want. I picked out the relevant things. So let's get started with this. Point estimation and confidence intervals are useful statistical inference for procedures. Okay, I hope you realize what's the difference between the two. Point estimation means give me a number. It's just a fancy way of saying give me a numerical representation of what you think a parameter value is. So for example, the point estimate of a mean is the sample mean, X bar, Y bar, that you. Confidence interval, we have constructed so many. A confidence interval, what is that? It gives you a range of plausible values for a parameter. So the whole point of statistics is a model, a probabilistic model, saying something has a normal distribution is the probability part. The statistic part comes in when you start saying things like, oh, yes, I say that y is a function of the predictive variables linked by some unknown parameter. That's what makes this a statistics problem. What makes this a probability problem is the fact that I say that this thing has a normal distribution. The error terms or the y's have a normal distribution. That's the probability part. The statistics part is when you start introducing these betas and things like that. And this is why, if you have done 313, I don't know whether anyone in this class has done 313 in the past. Anyone did 313? Statistics for data science. Oh yeah. What's the button for 313? I mean, this is not an exam question, but do you know? It's beta vector. It's the beta vector. And guess who chose that button? Yours truly. All right. Why? Because that's what statistics is all about. It introduces parameters. And so a confidence interval is a range of plausible values for a parameter. And you've learned how to find intervals. Okay. So the third branch of inference is hypothesis testing. And this chapter is going to give you some of the mathematical background of why we do what we do when we test hypothesis. Why do we say, oh, go calculate this statistic. If it is more than a certain value, then reject the null. Okay, we're going to give you some of the, we'll be more careful in why we do that. Think about why such a thing would make sense. Okay, so a little bit of notation first you must understand. First of all, most books tend to write this as omega is what we call the parameter space. Capital omega is what we call the parameter space. What do we have parameter space? Let's think about the simplest parameter space that we can consider, okay? The parameter space will be the place where your parameter values can reside. So if, for example, you're talking about a one mean situation, in theory, that mean value can be any real number. In that case, the parameter space is R, all the real numbers. The parameter space is the space where the parameter potentially could be. And so do you understand this notation? The noun says that the parameter theta is an element of omega naught versus each one. Theta is an element of omega 1. So let me clarify with a simple example what this could mean. If I were doing the case of a one mean problem, I might test this hypothesis, and you might have seen this kind of thing before. Mu is 15, okay, versus mu is not 15. This should be very familiar. Do you notice I have partitioned R into one dot union everything but that dot? Do you agree with this statement? I know it's weird. The real numbers is at every real number. 15 is a real number. This means this is this, the set that contains this number is that omega zero thing. Basically, hypothesis testing has various forms. So you may say, oh, but what about if I tested this hypothesis? How about if I tested mu is greater than 15? Then in this case, my parameter space is restricted because the union of 15 and more than 15 produces what set? It produces 15 to infinity right there, the parameter space. The important thing to note is that the space of the parameter values, omega naught, specified under the norm, union the space suggested under the alternative, I think they call it omega 1. The union of these two must always produce the entire parameter. And what the parameter space can be depends on the problem. The one that we teach in 115 and all that, we never see these things, of course, in 115 class. But when we write something as simple as this in 115, well, we're saying that mu could potentially be, and I'm just breaking it up into two statements like that, so that when I union this with this, I'm going to produce the entire parameter space, which in this context is R. But it doesn't always have to be every real number. Think about it. Let me give you a very, very simple example. Could I not, I know we didn't do this. We don't do this in 115 at all. Let's test this hypothesis, shall we? Mu is 2 versus mu is 5. Doesn't this look weird and funky? Okay, you're going to learn how to do things like that. We didn't do this. Why? Because you blow our brains out. But why? Actually, isn't this test much simpler? Yes. What's the parameter space here? Just two numbers, 2 and 5. You have restricted it to just only this and only this. It's just that we never seem to talk about it. This is actually a simpler test than this. And ironically, this is the established one that people want to learn. But we are going to start our consideration of hypothesis testing by actually looking at. Now, this is called a simple versus simple test. Why? A test is called, a hypothesis is called simple if it has just one value that the parameter can take. This kind, where it can be a multiplicity of values, is called composite. This is actually called a composite hypothesis. These are called simple hypotheses. That's the only one now. So we are going to start our consideration. Well, not exactly today with this kind of simple versus simple, but we'll be going to simple versus simple very, very soon. All right? Okay. So let's go on in the book. And of course, you can read. So a few things to talk about. How many of you have heard of type 1 and type 2 errors before? Yes. If you've gone to any stats class, you would have. Anyone care to tell me what a type 1 error is before I show you? It's in the notes. And this one, I expect only those who have gone to stats class know. Because if you have not gone to stats class, you really wouldn't know. What is a type 1 error? If I make the decision to do what? Does anyone remember that? Yeah, what's a type 1 error? If I decide, based on my data, the evidence on the data, I make the decision to. All right, reject the null. But the null is actually, yes, okay. So a type 1 error happens, right? A type 1 error happens, okay, do you see this table in the book? All right. A type 1 error happens when you see you are faced with two hypotheses. You have a null and the alternative. This textbook likes to use H1. Somehow I hope you can use HA. I think it's clearer for students, but it's the same thing. So, do you see true state of nature decision? Now, when I say true state of nature, I hope you realize we do not know the true state of nature. I always point this out in 115 club. If I knew the true state of nature, what am I doing testing a hypothesis? Go home. There's no mystery. I know the value of mu. Get out of here, right? I do not know the true state of nature, but I do have data. And the data guides me to make a decision. If I decide to reject the null based on what I see in the data, and it turns out that the true state of nature is that the null is true, was that a good thing? No, I've made a mistake. I have wrongly rejected the null hypothesis when I should not have. That is termed a type 1 error. And I think it's quite obvious what a type 2 error is. I accept the null based on, that's an informed decision. It's not a random decision. I accept the null based on my data, because that's all I have. My data is pointing me to accept the null. But unfortunately, the true state of nature is no. Actually, the alternative was true, so I made another kind of error that's called type 2. Now, this has to be firmly in your mind, at least for today. These two. Of course, if you are in a happy situation where the true state of nature matches up with the decision you made, that's good. So I hope you realize that the idea is we only are interested in hypothesis tests that will result in your being in the correct places most of the time. There will be times a test procedure will go wrong. But you do not know when that is because you don't know the true state of nature. So the whole point is you want to pick tests that in the long run will lead you to be in the correct places. That means when you should reject the null, you are. And when you should not reject the null, you are also not rejecting the null. You want to spend as much time in the correct places as possible. So I think, as with all things in life, it should be quite clear to you that you cannot fully win all the time. Think about it. Is it clear to you that if I tweak my test to make the possibility of making a type 1 error very low, what's going to happen? I'm going to show you, you can tweak any test to make the possibility of making a type 1 error very, very low. What do you think will happen when I do that? Because if that's the case, why doesn't everyone do that all the time? There must be a price to pay for doing that. Anyone guess what happens when if I try to make my test such that I almost never or even never make a type 1 error? What do you think, sir? Let's say what and actually let me ask you this. Can you give me a decision rule that will make it impossible for you to ever make a type 1 error? This is a very extreme question. Do you have any suggestion? What decision rule could you adopt that would make it impossible for you to ever make a type 1 error?
Maybe they just or like the null something not gonna be true.
That's a very good try, and you're on the right track. But you can't do that because you don't know the true state of nature. If I said, what? As I said, you make the decision to reject the null based. You choose to reject the null based on what you see from the. Is there some kind of blanket statement you can make that would make it impossible for you to make a type 1 error? What can you say? This is so on the nose. I think you all don't really know what I'm getting. What decision rule can you make that would protect you from ever making a type 1 error? Anyone know what I'm getting? What kind of decision rule would that be? It's very extreme, but what is it? How about if I said, I choose whatever I see, I will never reject the null. Is that a decision? It isn't. So I think the problem students say they don't understand what the word decision is. A decision is something like this. Remember when you calculated x bar minus what the null says, 15 over x. See, the problem is we get so bogged down with all the details that sometimes the decision is not. If you set up, let's talk about it. If you set up a test which has an alpha significance level, let's make it simple, one tail. Remember that we draw the normal curve, and then if you want it one tail, 5%, I think you should know this number, 1.6. That would mean that you calculate B and you say you reject the null if C is greater than 1.645. They've done this for so many homework problems already. Do you realize that the problem is this is a decision rule? Why? It means look at your data gave you X bar, compute this thing, and if it exceeds this, this gives you it's like a prescription on what to do. If I see this happen, I will decide to reject the null. That's what I mean by decision rule. Now, do you realize that every decision rule could potentially lead you to make the wrong choice? What is the justification for this rule? This means if really what you say is that the mean is 15, if truly the mean is 15, then once I standardize this thing, I should not be getting things very distant from 15. So I'll say this carefully. You say in the null that the mean is 15. If that is true, this will be normal 0, 1. If this is normal 0, 1, it is highly atypical to get something even bigger than 1.645 because that only happens how many percent of the time? 5% of the time. That's the, I'll say this again. You have a null statement. The null says mu is 15. You collect your data. I found my sample mean. Now, to make this really simple, let's assume we know what sigma is, so that I can use a normal 0. You also know from Math 365 that when you standardize, you turn a variable into a normal 0. You also know that the way the normal 0 behaves is that only 5% of the time will you observe normal 0, 1 things that are 1.645 for example. Therefore, if I take my sample mean and if you say this is true, or if what you say is true, then this standardized variable should not really exceed this a lot of the time. That is why if I do get something that exceeds this, this is unusual and rare. And the logic is, therefore, I doubt that what you said here, that mu is 15, maybe this is not true. And so I decide to reject it. Now, this happens very rarely when this is the case. So we will decide, the rejection rule is reject null when x bar minus 15 over sigma over f is more than 6 or 5. That's what you need. Of course, this can be made a little bit easier for people to parse by rewriting it as 15 plus 1.645 sigma over root n. This is a decision rule. So, what is the deal with a type 1 error? A type 1 error is this. When I see this, I'm going to reject it now. So, let's say I got an X bar that was, I don't know, 176. This is so far away from 15 that it's going to produce a Z statistic that's humongous. I'm going to decide to reject or not. In other words, the thing is, it is so unlikely to see a mean like 176 if truly the population mean was 50. But here's my question to you. Can it happen that your population mean is 50, but you did get a sample whose mean was 176? Can it happen? Yes, it can. And this is the essence of what a p-value is. The p-value is the probability of seeing this if this is true. Yes, the p-value will be tiny. It's very unlikely to see things like, but not impossible. And that is why every decision rule could potentially be wrong. Your decision rule says reject the null when your mean is too big, basically. Your mean is too big, reject the null. But I just showed you that even a large mean can happen when your mean is 50, when your population is 50. And so that essentially is why I say when the null is true and you decide to reject it, I think people are very confused by this table because they think if the null were true, why would I choose to reject it? And that means you don't understand hypothesis testing at all. You do not know the true state of nature. All you have is your data. Your data is guiding you to reject the null because your mean is big. But back in your mind, you must remember, even though my data was very unusual, it is possible. And that gives rise to the possibility of making a type of error. Therefore, back to my original question, how do I protect myself from ever making a type 1 error? What do I need to say about this decision rule? Go crazy, tell me. What decision rule will make it impossible for me to wrongly reject the null? I will never wrongly reject the null if I let's talk about life. If you don't want to make a wrong decision, what do? Make no decisions. Yes. So how do I never wrongly reject the null? Never reject the null. If I never reject the null, I will never wrongly reject the null. Do you agree? I know it's bizarre and weird, but that's what I'm trying to get at. And one practical way to do that is to say, reject the null if your x bar exceeds what? Infinity? This is like trying to please someone that cannot be pleased. Whatever you do is never enough. You are never going to get a mean more than infinity, which means you will never reject the null. Isn't that cool? If I never reject the null, I will never wrongly reject it. I have zero the possibility of making a type 1 error. What's the consequence of doing that? Why doesn't everyone do this? Isn't it cool? I've managed to bring down my probability of type 1 error to 0. What is the consequence of bringing a type 1 probability down to 0? Yes! Your type 2 error probability gets inflated. You can't win. Because if you decide never to reject the null, there are times you should. But you are stuck by your guns and say, I'm never going to reject null. I want to protect myself from making a type 1 error. I will never reject a null. But there are times when you certainly should have rejected null and you did. So therefore, one of the most important things to understand about hypothesis testing, there has to be a balance between your type 1 error rate and your type 2 error rate. It's not cool to have tests that have ultra low type 1 error rates because your type 2 error rate is probably going to be bigger. So that is why, have any of you heard about this famous significance level called alpha equals 5%? Why is 5% so beloved? And what is alpha, by the way? This alpha is the significance level. It is the benchmark that if my p-value was below that, I would reject the number. So I hope some of these 115 things are floating back in. If your p-value is below this prescribed value, reject the number. 5% is so loved by people. Some people think it's the only one you can have. It's because it gives a good balance between the two errors. If I pick this is not too big, it's also not too small. I mean, think about it. Why do people say at a significance level 0.00001%? That could be a thing. But if you pick a very small type 1 error rate, the problem is the factor grow. So picking 5% is a very sweet spot, which people like. That's one. All right. So this is the reason why we want to be careful when we do any test, not to do too much. Okay, so the book then goes on to say this. Look at 4.5.3. You reject the null if, see, they write it in a very, very abstract kind of way. X1 to Xn is an element of C. This is a very generic way of saying when I have my data going into what's called a critical region. When it goes into, when the value that you calculate from your data goes into a critical region, you will decide to reject the number. I have actually constructed a critical region here for you. This and above is a critical region. Why? If my x bar, see, x bar is a function of your data. X1 to Xn is your data. When my data is more extreme than this, in other words, all values after this are in the critical region. If my observed data enters the critical region, then I will make the decision to reject. That's what the book is saying. However, if I am not in the critical region, that's what they mean by C complement. It means I'm not in the critical region. You don't call it the acceptance region. It just means that I'm not in the critical region. If I'm not in the critical region, then I will retain the null. I will not reject it. So one important thing is I'm going to introduce this thing called the size of a test. The size of a test is the significance level. And it is defined as, okay, this is going to take a little bit of concentration on your part. What's the probability of you falling into the critical region when your value of the parameter is somewhere in the null hypothesis parameter space? Wow. All right, this is where things start to get a little bit difficult to parse. So let me go through definition of size or significance level again. It means what is the probability of your data falling into the critical region? And what's the maximum value of this probability as you go through all the values specified for the parameter in the null hypothesis? So let's give you a practical example immediately. Let's say my null is a very simple one. Mu is 15. This is a very simple omega naught because we've explained this. This just tells you your null parameter space is just the one number, just 15. Therefore, this definition becomes easier to understand. It means what is the probability of your data falling into the rejection zone, the critical space, when the value of the parameter is the value specified in the null. The word maximum disappears. You know why? There's only one value to think about. There's no, the maximum is this. If you look only at yourself, what's the maximum height of sample of size 1 is you. So this definition is broader than that. It allows for composite hypothesis. Let me explain. If I went on to a null hypothesis that was like this, And I know we have never seen this in 115, but it's a thing. This is a composite hypothesis. What this means is exactly that. The alpha here has a more difficult definition. It means as I go for all values of mu 15 and below, I need to evaluate what's the probability of me falling into the critical region as I cycle through all possible values of mu, find the one that it's a maximum. This is easier to comprehend when you have a simple hypothesis like this, because there's only one number to think about. When you have only one number to think about, there's no maximum to think about. It's just that number. All right. So how do you do this in a very simple example? Let's say I gave you a decision rule, reject the null if x bar is more than 17. This is a very simple example. I want you to reject the null if x bar is more than 17. And what was I testing? I'm testing mu is 15. Can anyone tell me what would be the definition of alpha in this case? What do I need to find the probability of? Alpha would be the probability of what? Look at the definition. x1 to xn is an element of the critical region. So I'm looking for the probability that, yes, yes, when my mu is, yes. So in this case, if I wanted to reject the null says mu is 15. The decision rule, the critical region starts at 17. This is saying alpha will be the probability that I see a mean 17 and above when the real mean value is 15. My question to you is this. How would you find this? Well, that's why you need some assumptions. If I assume that my x bar came from a normal distribution, and if the mean is what you say it is, it will be 15. And then you have your sigma square over n, that kind of thing. Doesn't this become a problem that you can solve from Math 365? Because you have your x bar, you have your x bar, which is a normally distributed random variable, and things like that. So you can actually compute what alpha is. All right. So at this stage, I think we should be able to work on this first group work for the day, which is this one. Let me give this out to you. And we will just do A and B first. Then I'll talk about C. Okay, we'll start with something a little bit more familiar. How do you find p-values of tests, first of all right? I don't mind telling you, you're going to need to calculate a standardized statistic that kind of looks like this. X bar minus the null of value over sigma over time. So you're going to have to do that to get the p-value, right? And because sigma is known, we will just use normal no t distributions to do it. If something's making you confused, just raise your hand. I'll come and help you. That's the purpose of such a small class, right? So I can look at where you're at and just help you with anything that you might not be clear about.
So it's like a section we can kind of,
They are linked, but they're different. They utilize the same equipment, so I don't blame them. But they are not the same. They use a lot of the same conductors. And there are links between the policy steps and the question. Okay, so you can, you know, so first of all, go find on so that what are you see and do it. So first thing is go draw it. No, draw a sequence. Get the 0.01 equal to the website. What is that? I think it was 1% of what's that. I don't want it's not. I don't know what that number is. It's like, I know what it is. It is 0.0. So check it people or anyway, the exact number. Is it 2.5? Don't think of it. No, that is good. So we need to check what is the quantum so that the period between what. So yeah, just hold it. Nine, yeah, close that. So your Z will be. So draw a picture that will help you with this. You just need that when you are at 2.1, you have, then the area of the bed is going to be just one. Mhm. Yes, and that's what it is. So when you want to form a rejection group, you do something like this. We know that this is standard normal under the norm. What does the null say here? I think I'm testing 70, right? So this thing has a normal 0, 1 if the null is true. And so we will reject the null if that thing exceeds that area. See, this aspect of significance level is not very well taught in book. That's why you're pause. P value is much more greatly emphasized. But this significance level thing is not. Yes, so you can say reject now if yes, if no first decision rules. It's still be this one. Reject the null. Now, can you just make it a little bit easier for people to write this as so give it a something when x bar is something like that. Right. Original. Good. So are you being yes, reject it out like that. And it makes it easier actually for even on you, and I'll tell you why in a minute. If you just write it this way, when your is more, you're giving someone just it's like someone who doesn't even understand probability can actually implement the rule. So I hope these things are gelling a little bit more. You have data, your data gives you your sample. And so what does the null say? Well, your null says something, and you should find your rejection rule is something that is at least possible. The null says mu is 7, right? Now, when you derive your rejection rule, what are you getting? X bar reject null if X bar is more than 70 something, right? Does that make sense? Yes, you see, can you, I don't know how Americans talk this way. Can you frame that, right? Can you, does it compute, right? It does make sense.
I guess I just still don't get the difference between this and like confidence interval.
They are totally linked. It's just that a confidence interval uses the fact that you can sandwich it with certain property to give you that and right. I think that's what.
So this one's like only setting one
Yes.
side.
This is actually linked to a one-sided CI, which we never teach in this.
Okay, so it is essentially a one side.
Essentially, you are constructing the ingredients for making a one-sided confidence. Yes. It's just that you're saying it in reverse. A one-sided confidence interval, that's actually very sharp, that's correct. You are constructing a one-sided CI for mu. Well, the opposite of. Because this is the rejection part. It is,
Yeah.
yes.
Yeah.
But I don't want to confuse the process. I don't want to say anymore.
Yeah.
But
No,
what I'm trying to say,
get it.
good.
Yes.
Yes. Okay. That's perfect. So now we can move on to part C. And this one, I want to ask you, okay, calculate the probability of making a type 2 error when you implement this test. Okay. So I hope it is obvious to you. Actually, no. Did I ask this question here? Let me ask you something that's pretty on the nose. What is alpha? This is not in this worksheet. Let me ask you, what is alpha in this testing regime that you have set up? You have said reject the null if this, right? Do you know what alpha is? Is this a trick question? Is this something you don't even actually have to do anything to tell me what the answer is? What's the alpha here? The alpha is 0.01. Do you know why? Because you have set up your decision rule to be reject now when X bar is more than, can you give me the number? 71? Oh, 70.55. Okay, let's just go with this one. What does the calculation of alpha entail? Do this for when mu is what in the norm? When mu is, what does the norm say? Mu is 70. How would you do this? If the mu is 70, wouldn't you standardize both sides and subtract 70? And what are you producing? You are basically producing back that 2.29 thing. Don't believe me? Go try it out. That's it. In other words, if I give you a significance level, I'm giving you alpha. There's nothing to calculate. Good. I think you are getting it. Okay. So now I want you to write down part C says, what's the probability of making a type 2 error? And read the whole question. When you implement this test if the real value of mu is 70.2. Now remember the definition of a type 2 error. A type 2 error happens when you decide to accept the null. Look carefully, right? A type 2 error happens when you decide to accept the null, but the state of nature is that the alternative is true or the null is false. I'm now telling you the null is false. Mu is actually 70.2, and you have made the decision to accept the null. I want to ask you a question. You made a decision rule, right? Reject null when x bar more than 70.55. Can you flip it on its head and tell what's accept null is what happens? Yes, accept null if x bar is less than 70.55. Can you write that down, actually? Accept null. I know there's a lot of people say we never accept it now. We don't reject now. I honestly like the way this book is done. It just got rid of all that language. Just say accept. We accept the null if x bar is less than 70.55. Very good. Therefore, can you compute the probability of a type 2 error? The probability of a type 2 error is what? Let's write down the definition. Type 2 error happens when you what activity, what decision do you make that warrants you having made a type 2 error? If you decide to accept now, but what's false? But the null is false. There is a true value of mu that is not the null value. Can anyone tell me what the true value of mu is? 70.2. Now, my question to you is, can you now translate this to a mathematical statement? Can you compute the probability of accepting the null when mu is 70.2? When do you accept the null? What's the rule? I will accept the null if what do I see? I will accept the null if what I see for x bar is less than 70.55. This is essentially the calculation that you are doing right now. So the probability of making a type 2 error is the probability of accepting the null when unfortunately the null is false and should be thrown away. Well, we didn't know that. But when I tell you mu is 70.2, I'm coming from what we call an omission position. I'm telling you that mu is actually this, but your data was unfortunate. Your data generated an X bar that was kind of small, and so you decided, because one thing you must understand in statistics, you do not know the parameter values at all. All you have in your hand is data. And my data gives me a mean like that was less than 70.55. All I can do is decide to accept the null. So this must have happened for me to have accepted the null. But the true state of nature, I am telling you now, so that you can compute the type 2 error is the true state of nature is actually. Now, here's your job. Do you know how to compute this probability? Go back to 365, right? Can you standardize, right? In other words, have I given you enough information for you to find out what this is probabilistically? Remember that when you standardize, you must subtract the mean, right? The true mean. What is the true mean now? That's right. You do not subtract 70. Do you know why? Because that's not the true state of nature anymore. So type 2 errors are always more difficult to understand. Because is it clear to the class? To compute type 2 errors, you always need to know actually the true state of nature. There is no calculation of a type 2 error if you don't know the true state of nature. In other words, the type 2 error probability is a highly theoretical concept. It is something that you do not in a lab. Okay? It's something you do as part of constructing a test so that you know whether your test is reasonable or not. If you are finding that your type 2 probability errors are huge for hypothetical values of mu that could be, then the test should be thrown away. It's a useless statistical test. The reason why you did all those tests in 150 is because those tests are pretty good. They do not yield super unreasonable type 2 error probabilities. Is it clear what you're doing? So type 1 errors are easier to understand. A type 1 error is look at your rejection rule. It is the probability of rejecting the null when your true state of nature really is what the null says, which is 7. And this we know how to calculate. But a type 2 error happens when, unfortunately, your data did not cooperate with you. Your data gave you something that would lead you to decide to accept the null. You accept the null because your data pointed in the other direction. But the true state of nature is something else. So to compute type 2 errors, you always need to be told the true state of nature. This is why we never ask these things in Math 150. There's no probability in Math 150. They don't even know what this thing is. Right? But this is a math stack class, so we're introducing these things to you. So go compute this, and I think, do I give you another one to try as well? Calculate the, yes, I do give you another one as an exercise. Calculate the probability of implementing this type 2 error if the real value of mu is 71. That's just an extra question just to see whether you understand what you've done. And after this, I'll give you some R code to illustrate. Is it really slow to do these things one by one like this? And the answer is yes. Can we do a bulk thing? So this bulk thing will be in the next group work actually. So I'm going to pass this out right now. All right. The next group work 21 is of course linked to 20. Right? Finish 20D first, because that will guide you. I always do it this way. I give students specific examples with actual numbers. Then 21 generalizes that a little bit, right? Yes, it's 72. You want true. Can generalize. You know, you're not able to. Because here you can actually give me a probability. The W error probability is something because I didn't tell you exact. Now I'm saying assume you know here twice. It's anyway, so the first one basically oh right? Only one because so this actually you have very close to so so actually this is kind of a like a work. It's a oh okay. This is not true. So sorry. Go back to the definition of what a country so a tattoo never so the tattoo never what about the yes settle but the true set of measures could as it goes not a specific number now I think and when with what happens now and the beginning of the no change because so this is true set of measures
Because we're stupid, we say, "Well, we like to ask."
that's right so this is 1% okay but also this was so just right there good then you have to study
Absolutely.
so probability of tattoo these things are quite categorized. No, that's the probability of appointment. Sorry. So that's why in it's probability of actual. That I find of okay. When do you take the factor? Just say explicitly. You bring the factor error rate side to accept or not. So it's the probability of acceptance or not. I don't know whether you're still ready to feel accept or not. I'm not saying the probability now is true. No one knows that probability. It's the probability of making the long way, the probability of making the decision to accept or not. That's right. But what's the true state of nature? Always put the true state of nature underneath the property that indicate what's the true state. True state of nature now is mu equals mu zero. I'm trying to beat you away from the specific one. See here I do the true state of nature is the property. And so we could actually come to the idea. Yes, actually. So now I'm saying the true state of nature is so can you go one more step? When do you accept the What do you see in your data that will make you decide to accept the number? See, the rule is reject null if see this. So it's the probability of when the true state of nature is yes or C1. Yes. You are told, okay, so this you notice this expression is not a number per se, but it is a functional. So just do exactly what you do instead of 71. Right? Right. So one takeaway from Anna, that's all for today. So if you're done, and just take away, do not confuse p-values and significance levels. P-values, I think this class is quite strong, right? Because this is something you learn from B1. But significance level is something you look at B1. Significance level is fixed. And it is a certain level alpha that you think that you will say, if I see this happen, I'm going to reject it now, and the probability of that happening. So that the significance level is actually fixed. It gives you the opportunity to make the decision. Right? So so just put this in probability. This is the PR of and then right. You don't need that anymore. You know what? You have used that information already, and it's exactly. But isn't this that's the definition of a CDR. Of general. Make sense? Very good. Thank you.